Okay, this is part two of rotation, and this time we're going to look at torque. First, let's define what torque is. So to get an object rotating, you need to apply a force to the object to get it to rotate. Placement of the force is also important. So if you take a look at this door, the hinge is here, the door swings to the left or up, and so we have two forces on there. They appear to be equal in magnitude because they're the same size vectors, but they're placed at different places. So from experience, you probably know that pushing on the door from when the further away it is from the hinge, then the easier it is to move the door. I use the word better here, but I'm not sure exactly what that means, but it moves it easier or moves it faster or whatever. But if you move that force inside so it's closer, then it's going to be more difficult to open the door. The distance that from the hinge to where the force is called the lever arm, and we designate that with an R because it is the radius of a circle. If this door was free to move around and all the way around, then it would form a circle. So that radius is directly proportional to alpha, which is the angular acceleration. That just means that the further out you push it, then the more it'll accelerate the door into a circle. And it also means on this picture that if we had these three forces all at the same place, so that means R is going to be the same for all of these. The force that is perpendicular to the door will cause more of an acceleration than either one of these. In fact, this force D, logically, if you push the door at the end here, it's not necessarily going to move at all. So the direction is also important. So that's what this indicates. And so the definition of torque is the product of the force applied and the perpendicular distance. So we have this product, which means we multiply force applied, which is going to just be a force in newtons, and the perpendicular distance from the axis of rotation, and that's what we're going to call R. So on this screen we have we define the formula. So we're going to use a lowercase Greek letter tau. It looks like a small capital T that's smaller, and on your formula sheet, tau is equal to R perpendicular times the force. And if the R is not perpendicular, or the way to make R perpendicular is we're going to use the sine function. So if we get an angle, we're going to take the sine of the angle. We'll see how that works in an example in a moment. The strange thing about torque is that it's measured in a unit called meter newtons, because radius is measured in meters and force is measured in newtons. The sine of an angle doesn't have a unit, so we call it meter newtons. There's no shortcut for that. It's common in the metric system to call it meter newtons. In the English system, it would be foot pounds, and you could talk to any mechanic about torque and the unit of foot pounds, and they would know what you're talking about. We also will have a direction of torque, and that will either cause a clockwise motion or a counterclockwise motion. And of course, as mentioned before, those are arbitrary directions. But looking down on this, clockwise would be moving it around this way, and counterclockwise that way. So let's try a problem. You should find this on your practice sheet. If the force of A is 25 newtons and the radius of A is 1.5 meters, and then the resulting torque. So we're going to use this formula, and we'll use it directly as RF sine theta. So we already have meters and newtons, so we simply plug that in. But what is the angle between R and F? So R goes out this way, and F is perpendicular to it. So the angle is 90. And as you remember from trigonometry, the sine of 90 will be 1. So in essence, if R and F are already perpendicular, we can just ignore the sine of the angle in the formula. So this calculates to 37.5 meter newtons. We'll see how this works on the acceleration on the next lesson, but right now we're just talking about the torque. Now, if the force of B is 25 newtons also, just as that one is, but it's at a distance of 0.5, the resulting torque will then, of course, be smaller because it is closer to that. So that means it wouldn't cause the door to open as quickly as the torque that's on the outside there. Okay, so for our next example, if we have the axis of rotation is on the end of this stick, and we have these two forces. So if force A is 30 newtons and force B is 20 newtons, they were both exerted on this meter stick as shown. Which exerts the greater torque? So we just go ahead and calculate them separately. Let's do the A one first. The radius of A looks to be a half a meter, because this is a meter stick. Is 1 meter, because it's on the end of the meter stick, and the force is given here as 30 newtons. But it's not perpendicular, so we have to account for that. We need to have the perpendicular force, the one that goes up and down here. So we're going to say 1 meter, and we want the component that goes up this way, and so we're going to use the sine function because that would be the opposite of the 30-degree angle. So 1 times 30 times the sine of 30 comes out to 15 meter newtons. All right, let's try the other one. Let's try B. So B is already perpendicular, but it's at a half meter, so it's 0.5 times 20, because it's at 0.5 meters, 20 newtons, and sine of 90 is 1. That comes out to 10 meter newtons. So even though the force of A is, another third larger than the force of B, this is how it comes out. Okay, so here's another concept, and that is when there's more than one torque acting on an object, then we actually can add them together to get what's called the net torque. So we have the torque on the outside of this. This is set up so that these two wheels are connected to each other. They're two thin shaped wheels of radius A. The inside one is 30 centimeters and the outside one is 50 centimeters. They're attached together on the axle, which is right in that solid dot there, passes through the center of each. And we're going to calculate the net torque in each, if each force has a magnitude of 50. Okay, so you're just sort of setting it up this way. So the net torque is the clockwise torque, right? That's going to be the one that goes around this way. So that's going to be the FB. And then we're going to subtract I got the clockwise and the counterclockwise backwards. Well, we just arbitrarily choose a positive and negative, but in essence we're just going to subtract these two because one's going clockwise and one's going counterclockwise. Plugging in the numbers, we have 0.3 for this RA and 50 newtons, and it would be perpendicular to the radius, so it's a sine of 90. And then we have 0.5 meters and 50 newtons, but now we have the sine of 60. And the reason we use 60 degrees is that we want the component that's perpendicular. So we don't want to do the, if we use the sine, we would get this up and down force, but that isn't going to be in line with the radius. So we want the one that's opposite the 60-degree angle. So be careful which one you choose, and always make sure that the force that you're calculating, or the component of the force, is perpendicular to the radius. Okay, so doing those calculations, then the sum of all torques comes out to 6.65 meter newtons in a clockwise fashion. Oh, it's going to go around that way. The next example talks about rotational equilibrium. This is when the net torque equals zero. So equilibrium means that it's not moving, and rotation means it's not moving in a circle. So if we take this seesaw, we've got two forces. We've got clockwise force, and that's clockwise torque. It's going to go around this way, and when we have the counterclockwise, it's going to go around this way. They have to be equal because the net torque is equal to zero. So those two torques are going to be equal. Not the forces, but the torques are going to be equal. So the mass on the left is 5 kilograms, and the mass on the right is 12. Okay, no problem. If the mass on the left is at 45 centimeters, where do we put the mass on the right? So this big mass, we're going to put it someplace so that the torques are equal. So we simply just set it up for the torque left is equal to the torque right. Torques are, these are both the distance from the axis of rotation. These are both going to be perpendicular. So we can just ignore the sine on both of them because we don't need components. We can just use them directly. So I label this the radius of the left one times the force of the left one equals the radius of the right one and the force of the right one. Now I plug in these three numbers that I have, and I can switch to meters because I want to get my units as that. And the force, remember, is going to be the mass times 9.8 because we want the weight of each one of those. So we put 5 times 9.8 and then 12 times 9.8. We're doing the math. We're going to multiply the things on the left, and then we're going to divide it by the 9.8. It's true that the 9.8s both cancel. And it wouldn't matter if we left it in centimeters because then our units are just going to be centimeters. This calculation comes out to 0.187 meters, which is about 18.75 centimeters. So probably I should have just left these as 45 centimeters, and then I wouldn't have had to do that last conversion there. So it's reasonable to say that if this small torque is out here at 45 centimeters, or this small mass is out here at 45 centimeters, the larger mass would be closer in. It's sort of like the teeter-totters where you've got the small person sitting way out here and the larger person closer in, and then you can balance. Okay, so that's the end of the torque. See if you can do the problems that are assigned. Ask me questions if you have, and thanks for watching.